So yeah, I just wanted to give a talk on how we are using specific, like one of the TEs that I've been working a lot on this year, which is secure multi-party computation. Let's go. So let's start with a quick overview of what does Worldcoin actually do. For those who don't know, what we're doing is we are issuing people proofs that they are unique human beings so that they can use it in the blockchain domain. And why is this useful? It is useful because you can distinguish between bots and real human beings. And this is a bit of a missing primitive. Like having been in the space for a while, quite often you hit this problem where, okay, I need to make sure that there is a single human that can cross this gate and not multiple people. You want this, for example, when you're building a voting mechanism on chain. But you also want this, this is sort of end game airdrops as well. We're now having these airdrops where people come up with more and more elaborate metrics to make sure that people don't claim more than their fair share. And then people find more elaborate mechanisms to game this system. The end game here is that you just want to make sure that, okay, this human gets to claim this once, no matter what kind of trickery they may be doing. We're also now in the age of pretty sophisticated artificial intelligence and actually distinguishing through online interactions who is a human and who is a bot is becoming a very hard problem. So that's another area where we are anticipating this to be a very important technology. And basically with the world just getting more and more digital, we want to make sure that the concept of humans is adequately represented and can be built around. Now, how have we solved this problem? We've solved this with irises. Turns out that the human eye has very unique random patterns. They're not genetic. They're unique to every individual, kind of like a fingerprint, but with much higher entropy. So these are the best ways to distinguish humans. It is also, as we will see, something we can do in a very private manner. And there's some alternatives out there. You might be wondering, like, why not use passports? Why not use fingerprints and so on? Turns out that none of them actually scale. Either they are too easy to circumvent, you cannot do them in an automated fashion, or in the case of fingerprints, fingerprints are only unique up to 1 million people. Now, given this context, we need to build a system that can achieve that. And we have our little toolbox. We have a toolbox full of very exciting privacy and trust enhancing technologies. And the approach we're taking is known as defense in depth. We're not going to rely on a single piece of technology here. No, we're going to stack them one on top of each other. We're going to build multiple layers that even if one breaks, we still have all the privacy and anonymity guarantees we want in our system. This is kind of a high-level, simplified overview of how we do that. Let me quickly run through it. I won't go into too much into details in this talk, but basically a user goes to an orb, which is this, I think we have one on around here. There you go, that's an orb. So this is a hardware device that we've developed. You can install a wallet, go to the orb. The orb will then use sensors to make sure that you're a real live human being, and it will take a picture of your irises. It will sign that using its hardware key, and then send it back to you. Now you have an authenticated image of your irises on your, in your wallet. What you can then do is create a zero-knowledge proofs that derives this iris code, which is like a machine learning algorithm that extracts the entropy. You can derive this iris code in a zero-knowledge proof. Then you can turn that into 3 secret shares, and you can send those secret shares encrypted to our multi-party setup. So these are 3 separate entities that run a cryptographic protocol that allows them to together verify that a piece of information they've received is a unique human, corresponds to a unique human being. And they can do that in a way that none of the parties learns anything about the secret itself. So the important thing that we've achieved here is that You basically go to an orb to take a selfie. The selfie doesn't get revealed to anyone but you. And then you derive these secret shares that also individually don't reveal anything. And you interact with this multi-party. And what you get back is a proof that you haven't signed up before. With that proof, you can go to Ethereum and you can have your public key added to a set that lives on Ethereum. And this is where defense in depth again comes in. To then use this system, you generate a proof again that you're in this set. So, to recap, after you've signed up, every time you use the system, there's another layer of defense that re-anonymizes you. All that is revealed is that you did sign up before, but it's not revealed when you signed up, which public key you added, and so on. So these are the layers of the system. The MPC itself, let's see. Yeah, I'll get to that in a moment. So there's a lot of technology here that comes together. We have the Orb, which is this hardware platform that has very sophisticated tamper protection, it has very sophisticated liveness detection, and so on. Then we have an artificial intelligence work stream that is all about doing this iris code magic, about distinguishing. Then we have client-side zero-knowledge machine learning to do the derivation of the iris code from the raw image. Then we use multi-party computation to solve the global state problem of verifying uniqueness. Then this MPC itself, we actually run inside a trusted execution environment for reasons I will get into in the next slide or so. Then a couple more work streams just for completeness. We're working on a vector database. We have this anonymous extra level protocol, and we're using a ZK rollup style scaling solution to make this whole thing work at scale. Now, like I mentioned, we need to do, we do as much as we possibly can client side, and this is where you want to use ZK. But sometimes you have global state. In this case, we have a uniqueness constraint that we need to solve, which is global state. There's a couple of approaches you can take there, FHE, MPC. Within MPC, you have many variants. We pretty quickly converged on linear MPC in the semi-honest scenario, mostly because this gives us the performance that we need. And we'll see soon enough why that is important. The problem with semi-honest MPC is that you have a mild trust assumption on the parties that they run the protocol correctly. And in order to solve that trust assumption, we layer it in a trusted execution environment. So before the parties initiate the MPC protocol with each other, they attest that the other parties are running the correct software. I'll skip over how we actually compute iris codes in MPCs, but just want to highlight that linear MPCs are surprisingly simple. Before I got into this in earnest, all I knew about MPCs was Jao's goblet circuits, and linear MPCs are just so much nicer. But the TLDR here is you end up with a scheme where you have a little bit of computation overhead per party, and you have a lot of communication overhead. Basically, every multiplication you need to do means you need to communicate with your other parties. Now, what's the scale we're talking about here? These are actually slightly old numbers. We're even larger now, but more than 10 million users, 6 million of which are biometrically verified. And we're doing about 1 verification per second sustained and up to 10 per second at peak capacity. Now, what does that mean? You can look at the memory requirements for just these iris codes. We have 6 million humans, they have 2 eyes, we have 2 vectors per eye, we have 12,800 elements per vector, and we encode them in 16-bit elements, so we need half a terabyte of memory just to store the database. The performance requirements actually make it such that we need to store all of that in GPU memory to be able to hit our throughput. Yeah, compute, same story, you'll end up with more than 400 tera field operations per second. And the interesting, actually the biggest bottleneck for us is the bandwidth that the multi-party compute requires. So we have some very clever tricks there where we make use of the linearity of the MPC to reduce the amount of communication by a factor of 12,800. But we still end up at capacity, so 20 verifications per second, which will be the peak throughput. We still need to do almost 4 terabyte bits per second of communication bandwidth between the parties. Benchmarked a lot of different compute solutions here, and it turns out that the most cost-effective that we can do here is use H100 GPUs. This is kind of interesting because these are very expensive machines and they're very in high demand because of all the AI that's going on, but despite the high price, they still give you the most compute for money. So that's what we implemented on. We implemented the whole MPC scheme in CUDA. In the process, we found some bugs in CUDA itself, which have now been fixed. Specifically, and this is kind of interesting too, we've deployed this on AWS, and AWS has these P5 large, and the hardware that they use is different from the hardware that NVIDIA provides out of the box. If you just get an NVIDIA H100 cluster, which is pictured on the left, it has 8 of these GPUs in it. The way they are configured is they have very good GPU memory bandwidth, and AWS changed that and dedicated some PCI lanes between the GPUs directly to the network interfaces, which is actually great for our use case because we are able to run our network directly from GPUs. We also have the whole encryption stack running in CUDA. So the network connections are from GPU directly through the network interfaces to the other GPU, and we need this because we cannot actually hit the 4 terabits if we have to copy to system memory first. So yeah, fun. It's been a fun exercise to get this infrastructure at scale. And this is only for 10 million users. We need to get to 1 billion users. Obviously, this doesn't work with our current approach where we basically do a linear scan to the database. You can do the math. If you do a linear scan through the database for each user, the amount of users will grow, but the amount of users who sign up will grow as the first derivative. So what you will get is that your resource consumption even grows quadratically with your user size. So that's not sustainable. And that's why I've been looking into running factor databases in MPC. Should have that done by the end of the year. Yeah, hierarchical navigable small worlds is what we're looking at here. That should get us to logarithmic scaling and maybe even get us off the GPU platform. And that way we should be able to scale this to 1 billion people while maintaining the same uniqueness guarantees and same false negative, false positive rates as we are currently trying to achieve. Let's see, yeah. There's a lot of content out there about us already. You can check our white paper, for example, where we've detailed a lot of this. There's a lot of it also still in the works, so if you have deeper questions, please find me. And thank you all for